Okay, I think we'll get started as people come in. So thank you everybody for coming. Can you hear me? The look sound good? Okay. Thank you everyone for coming and welcome to the John and Violet K Fellowship Symposium. I'm Dr. Chan, the Director of the Research Program here at Iolani School. While these are unprecedented times that prevent us from gathering together in the same way, can we mute? I can hear some background. Amy, can you mute? Oh, thank you. Um, we are so happy that you can join us via Zoom, and hopefully you're enjoying your lunch in your own space, maybe by the tents. So John Kay, or Papa Jack, was a teacher at Iolani School for 52 years, and the wet lab came out of his vision to support research opportunities for students at Iolani. He also endowed the John and Violet Kay Fellowship, which provides a stipend and monetary support for a summer research experience. So Braden and Lico and the rest of the K Fellows this week wrote research proposals last spring and were awarded the fellowship of $500 to do their research. So yes, they got paid to do their research and you can too. So please contact me if you're interested in applying. Okay, so now I'll let Braden take it away and tell us about his research. Thanks, Braden.
Hi, my name is Braden Lee, and I did my project on the development and analysis of low-cost wireless flash memory devices. First, I'd like to extend my thanks to Mr. K and my mentor, Dr. Adonis, for making this project possible. In the midst of the COVID-19 pandemic, individuals were able to use distance learning tools such as Zoom to connect with one another while maintaining physical separation. These applications take advantage of the existing 4G LTE and Wi-Fi wireless infrastructure to provide virtual connections. Countries reliant on systems of mass transit have implemented an RFID and NFC capabilities in cards to allow contactless payment. The popular AirPods use the H1 chip embedded within for Bluetooth functionality to allow the wireless transfer of audio. On the hardware side, flash memory has become increasingly relevant as it carves a niche out for itself in the memory market. The term flash memory refers to a specific variety of computer memory that retains information after losing power and can be electrically erased and reprogrammed. Perhaps the most prolific application of this technology is the USB flash drive. Within a time span of 16 years, the worth of the flash memory market has increased over 550 times in value. Within the context of this presentation, the term flash memory device will be synonymous with flash drive. Given this prevalence of wireless technology and the relevancy of flash memory devices, I wanted to test the applicability of wireless technologies in a flash memory setting. I divided the project into two major phases: building and programming a functional model for each wireless-enabled device and the testing of each device to determine their use cases. Each model would be evaluated on its range, power consumption, and data rate. I aim to produce 3 models for wireless flash memory. The first Bluetooth-enabled, the second Zigbee-enabled, and the third near-field communication-enabled. Each of these technologies had traits that I believed could translate well in a flash memory environment. Although both Bluetooth and Zigbee share the same IEEE 802.15.4 protocol stack, meaning they operate similarly, they are both developed for different uses. Bluetooth boasts the largest range of the trio, clocking at approximately 100 meters, in addition to the widest implementation, existing in nearly every phone and computer. For reference, a meter is approximately the distance of one large step. The range of Bluetooth is approximately the height of Big Ben. Zigbee, on the other hand, has a significantly lower range and instead focuses on lower power consumption and the affordability of the technology. Zigbee is generally considered to cost less than 10 cents per foot, which includes the cost of wireless boards and installation. For reference, a typical Bluetooth transceiver costs about $1 and an NFC chip costs about 25 cents per unit. Near-field communication, or NFC, operates only within 10 centimeters of its target, but is granted resistance to certain cyber attacks thanks to its limited range. Phase 1, the simulation of a wireless-enabled flash memory device. To simulate the function of a flash memory device, I began with the hardware. The hardware of a typical USB flash drive can be grouped into 3 segments: the processor, the storage, and the communication interface. For my models, I used commercial off-the-shelf parts to simulate these functions. The Arduino Mega would act as the processor and a micro SD card as the storage. The communication interface would differ for each iteration. On the receiving end, I used a Raspberry Pi or a single board computer to collect the data. For the Arduino and Raspberry Pi to communicate and transfer files, there are a number of protocols and procedures that are put in place. If we take the example of Bluetooth, there are three major processes in play: Bluetooth, serial, and Z modem. Each of them is integral in facilitating the successful transfer of data. These terminology will be relevant for the rest of the presentation. Bluetooth is a wireless technology standard, meaning it establishes and preserves a wireless connection. On both sides, it opens a port for communication to travel through, on the Raspberry Pi being a RF COM port, and on the Arduino being a serial port. Under the guidelines for Bluetooth, it establishes a wireless personal access radio connection on the ISM band, or with a frequency of 2.4 to 2.5 megahertz. Serial refers to the process of transmitting data across the connection established by Bluetooth. Specifically, serial defines the data is sent one bit at a time. Z modem is a file transfer protocol designed for use over serial that handles the preparation of data for transfer and the interpretation of received data. On the transmitting side, Z modem divides the file into blocks for transmission using the serial process. When bits are received, Z modem assembles the file on the receiving end. Although Z modem was developed over 30 years ago, it still maintains relevancy. As opposed to similar protocols such as X modem, which waits for an acknowledgement message from the receiver before sending more data, Z modem sends data in a constant stream until the receiver detects an error. The protocol also allows file transfer to resume from the point of failure and auto transfers file, meaning the file only needs to be requested once. Furthermore, all file transactions are protected with a cyclic redundancy check, or CRC, a mathematical function that verifies the integrity of the data. These qualities make Z modem an efficient and secure method to transfer files. Here's a model of how Z modem would transfer data. After acquiring all the necessary parts, I designed a circuit to serve as the hardware simulation and act as the base of my programming. The Arduino Mega would act as the main processor for my flash memory circuit. Although there are two microcontrollers, the Arduino Mega and Arduino Uno, only the Mega handles the processing for the simulated flasher. The Arduino Uno instead only serves as a measuring tool to collect data output from the INA219, shown here in the middle. The micro SD card module acts as the storage for the device. The HC05 provides Bluetooth functionality to the circuit. The INA219 is similar to a multimeter in that it is an intermediary inserted between a section of wire. As electricity flows through the INA219, it measures its voltage, current, and power. This data is then sent to the Arduino Uno for collection. Note that the HC05 is wired to two ports on the Mega labeled TX and RX. These pins represent the input, RX, and output, TX, of the Arduino serial. By wiring these ports to the respective TX and RX pins on the HC05, the serial data is rerouted for transmission over Bluetooth. For the transmission of Zigbee, I used the Digi-XB3 module. The XB circuit uses the same concept as the Bluetooth circuit, the only difference being the XB module takes the place of the Bluetooth module connected. Although I originally intended to produce an NFC flash memory device, I was ultimately unable to produce a fully functional model of an NFC-enabled flash drive as a result of time constraints and programming challenges. I also experimented with radio frequency identification, or RFID, a wireless technology extremely similar to NFC, but was unsuccessful since the model requires two-way communication in which both the transmitter and receiver can talk to each other, but RFID only supports one-way communication. Next, I began programming the software for each device, the lengthiest step in my process. Before beginning, I established that the program must be capable of accessing data from the micro SD card and transmitting it over serial with the Z modem protocol. On the Raspberry Pi, I installed the program Minicom, pictured on the bottom left, to receive the data. For debugging purposes, I tested my program with a USB cable connecting the Mega and Raspberry Pi. After many failed iterations, I developed the working program. At the start of the program, the Mega initialized the micro SD card, the code for which is pictured in the middle, and established connection. Upon connection, the Mega would then send a list of commands to the Raspberry Pi, including options to move or print a list of files. Typing SZ followed by the file name would prompt the Mega to start Z modem communication. During the transmission process, the Uno recorded voltage, current, and power values from the INA219. The next step was to apply this process to the different wireless models. Since I had rerouted serial communications to the 8CO5 and XP earlier, I could apply the same program for my Bluetooth and Zigbee model given the proper configuration. For Bluetooth, I established first a Bluetooth connection to the 8CO5 and the Raspberry Pi, after which I could use an RF COM port for communication. For Zigbee, I used the configuration software XCTU to allow my two XE models to discover and connect to each other. Phase 2, the evaluation and analysis of flash memory models. For the evaluation portion of my project, I measured 10-foot sections along the side of my house. At the start, or distance 0, I set up the receiving device, the Raspberry Pi, and connected it to a laptop. With the OBS software, I was able to use the laptop as a display for the Raspberry Pi and record the transmission results for later analysis. 10 meters away, I set up the Bluetooth model and prepared for transmission. On the Raspberry Pi, Minicom calculated the data rate, and the Arduino Uno and computer terminal, the code for which is shown in the bottom left, recorded the power values into an Excel spreadsheet. For every data transmission, I used a 100 kilobyte large binary file. At each distance interval, I would begin the transmission and record the receiving end with the OBS software. Then I verified that the data was transferring to the receiving end. If the Raspberry Pi ran into errors, the connection was too unstable for data transfer. I would then move 10 feet back and repeat this process until the data transmission cut out. After completing all of the trials, I organized all the data in an Excel spreadsheet. Using the recording for OBS, I logged the BPS at 100 millisecond intervals for each trial. With this data, I was able to construct graphs comparing the power and data rate to the distance. Zigbee was only capable of transferring data successfully up to the 40-meter mark. At 50 meters, the connection became unstable. When I first started the program, I was unable to initiate Z modem transfer. After trying again, the program was able to establish a connection, but the data received was incomplete and the process quickly timed out. Although Bluetooth continued to successfully transfer data up to the 70-meter mark, I was unable to test further since experimentation was constrained by the length of my yard. During the transfer process, Zigbee had a significantly lower power consumption than Bluetooth. Furthermore, while Bluetooth had a spike in power consumption as distance increased, Zigbee maintained a generally linear function of power consumption. On the other hand, Bluetooth had a significantly faster data transmission than Zigbee. A difference of this degree means Zigbee file transmission would be noticeably slower than Bluetooth. While Zigbee was only able to maintain a connection within 40 feet, Bluetooth was not only able to reliably transfer data, but maintained high data transfer speeds until 70 feet. Although the range and data rate of Zigbee is inferior to Bluetooth, the low power consumption provides a compelling argument for Zigbee, as Zigbee flash drives will last longer on a single battery charge than a Bluetooth flash drive. Coupled with the other merits of the Zigbee technology, such as cost effectiveness, this technology holds great potential for future implementation in flash memory technology. Current Bluetooth flash drives on the market can cost anywhere between $60 to $130, whereas a basic USB flash drive typically costs less than $15. A Zigbee flash drive would cost much less, granting it the potential to meet the demands of a consumer base invested in the wireless capabilities but repelled by the expense of Bluetooth flash drives. However, the technology still has some obstacles to overcome. The existing infrastructure and wide implementation of Bluetooth allow the technology to take form in a flash drive, whereas Zigbee implementation is scarce and remains a widely unused technology. Although add-ons could be manufactured to provide laptops or phones Zigbee functionality when plugged in, it would hinder the convenience of the technology. Therefore, while Zigbee has the greatest potential for implementation in flash memory technologies, the existing infrastructure of Bluetooth makes the technology the clear choice for contemporary implementation. Although not to the same extent, NFC has seen significant implementation within phones and some laptops to accommodate the broad usage of the technology in mass transit and contactless payment. Given this existing infrastructure for contemporary implementation, it would be worthwhile to evaluate the use cases of this technology in comparison to Bluetooth, especially considering the stark contrast in working distances for the technology. Based on my time working with the technology, I would consider using X modem technology instead of Z modem. Since NFC uses half duplex communication, meaning only one device can be talking at a time, Z modem's method of sending data uninterrupted until a negative acknowledgement is received would not work, since the receiving device would be unable to send the NAC message when the transmitter is continually sending data. Instead, X modem's process of sending data one block at a time and waiting for an acknowledgement message must be applied, alternating each NFC device between active and passive. Another possible topic to explore is varying baud rates. For my experiment, I used the 9600 baud rate for all communications, although it may be worthwhile to examine how varying baud rates affect communication. Although I only implemented Z-modem, I investigated a number of serial file transfer protocols during the research portion of my project to determine the optimal choice. I also learned the minute differences between various wireless technologies and how they translated over into the program. Although at first glance, it may seem Zigbee and Bluetooth are near identical since they share many of the same protocol definitions, I soon learned that they both require different configuration methods when debugging. Finally, I learned to appreciate the complexity and seeming simplicity of an object as common as an SD card. While working on my program, I ran into trouble accessing the files on a micro SD card. In an attempt to remedy this problem, I studied block storage methods and FAT32 for micro SD cards, which I was able to repair the library functions. My project would not have been possible with the irreplaceable support of so many individuals. Thank you to Dr. Chan, Dr. Ordonez, Mr. Yamauchi, Mr. Hayashi, Mr. Aylmore, Dr. Inouye, and Papa Jack.
Awesome. Thank you, Braden. And now, if anybody in the audience has any questions, feel free to unmute or type it in the chat. We've got about 4 minutes until Liko's presentation. And you can stop sharing too, if you're, yeah. You can turn on your video as well.